All right, let's get started. Welcome, everyone. So excited to kickstart the semester with the first robotics seminar of the fall with Professor Trevor Darrell. I'll be introducing the speaker and then I'll pass on the mic to him. So Professor Darrell is on the faculty of the CS and E divisions of the ECS department at UC Berkeley. He founded and co-leads the Berkeley Artificial Intelligence Lab, or the BEAR Lab, the Berkeley Deep Drive, or BDD Industrial Consortia, and the BEAR Commons program. Darrell's group develops algorithms for large-scale perceptual learning, including object and activity recognition and detection for a variety of applications, including autonomous vehicles, media search, and multimodal interaction with robots and mobile devices. His areas of interest include computer vision, machine learning, and multimodal natural language processing. And we're so excited to hear from you, Trevor. Take it away.
Cool. I think this will work. Thanks, Andrea, for the wonderful introduction. It's great to be here and be in this new building and this new auditorium. Great to see all the new infrastructure at Berkeley, at MIT. We have wonderful new buildings too. And this is a fun talk to give. I'm really excited about everything that's happening in vision and language and robotics, and also to give this talk at MIT. And there's a structure to my talk. I'm going to actually spend the first part talking a little bit about philosophy and what does it mean to be vision and language and robotics, and which dominates the other. Hopefully I'll provoke some MIT people in the room. We'll see if that happens or not. And then maybe most useful will be some of the new tools and tricks that I'll talk about that we've been building at Berkeley that I think are driving new capabilities for robotics that are really exciting. And then last, I'll tell you the direction that my lab is betting on for the future, which is sort of trying to blend the paradigm of large-scale pre-training with bottom-up structure from traditional computer vision and computer graphics, sort of a 4D conjecture. But first, let's talk about philosophy, and let's, really get to the heart of the triggering, existential angst of what is robotics, and does vision a subset of robotics, or is robotics a subset of vision, right? Which is it? Which contains the other, right? We've seen so much now. So many vision people are actually moving to robotics. It's kind of crazy. And why is this happening? Why are all the computer vision people suddenly becoming roboticists? Is it because robotics has all the unsolved problems? Data at scale solves vision, so let's go see if data at scale solves robotics. Is it because vision people want scary demos? We want humanoids stomping around our lab, looking ominous, creating the fear in our funders, just like the roboticists? Or I just gave this talk at RSS as a keynote, and I was like, or you guys still have conferences that fit in one room. And this is amazing. This is like ECCV was, less than 10 years ago, and I loved it, and I like the sense of community. And at that conference, there was a distinct sense of worry. The day before I gave my keynote, there was a panel on the future of RSS, and they were conjuring up future visions. And one of the future visions was why ICRA was acquired by CVPR and RSS was acquired by NeurIPS, right? Is our vision and ML going to just dominate robotics in the future? There's no, just like they maybe did for computer vision and NLP. Or conversely, will I argue that vision is just contained within robotics, right? Robotics is actually the larger problem. Well, what do you think? This is the beautiful image of a state-of-the-art humanoid robot, right? This is currently the future in 2025. Everyone's diving into humanoid robotics. I wonder how many people actually recognize this image. There's only one person in the room for sure, maybe two, who actually know where this image came from, and so hold your comment for a second. Is this in fact, it looks to me like it just came out of a Gen AI mid-journey renderer of, what was the prompt? Humanoid robot 2025? No, this is actually the cover of a book. Anybody, aside from professors in the room, know what the book was? By a famous MIT professor, Bertolt Horn. This is, in fact, the textbook that I learned computer vision from so many decades ago. And this was what we call robot vision, clearly for humanoids, or in the direction of humanoids, far, far away. I don't think anyone, this was like science fiction back then. And machine vision then clearly didn't have anything to do with robotics, the way we would call it robotics today, right? This is the syllabus from, I guess, 2004. This is all just like meat and potatoes computer vision, no humanoid robotic control, yet this is called robot vision. So what happened? Vision was part of robotics way back in the day when I was originally trained. But it all changed just around the turn of the millennium when social media and the internet redefined it. And in some sense redefined it usefully. Without the internet, we wouldn't have had all the progress in machine learning and computer vision, both ImageNet and Common Crawl, and the resulting vision and language models that they led to. But now maybe we're seeing everything come back together, which I think is a useful thing, the unification of vision and language and robotics. And I'm pretty happy about that. So I wouldn't worry too much which one contains the other, subsumes the other. I think it's all the same thing, and the core challenges of each subfield are still quite apparent. So that's one first bit of philosophy that I wanted to deliver. Don't worry about which is which. The second bit of philosophy I wanted to discuss is actually somewhat inspired by a lot of the conversations I've had with Phil Isola over the years. We've each independently been thinking of these ideas. And it's before we even get into the nitty-gritty of multimodal models, let's just imagine what do actually blind models see. What does a text-only model see? Can blind models, just a regular LLM, text LLM that's never seen pixels, is it visually grounded? Well, if you had asked me this like 3 years ago, I would have been like, nope. I don't know what you're talking about. Grounded, I know what grounded meant. Grounded is like a language person's term to say it is something connected to a real signal in the real world, like a robot, right? And these LLMs, they might have been really cool back in 2022. They were like amazing at textual translation and reasoning. And like, while there were some vision people who were really anti-vision, especially at Berkeley, anti-language, especially at Berkeley, even they would admit that language was useful to define tasks. Like, you don't want to refer to category number 25, you'd rather refer to orange ball. But they're not grounded in any real way. We then would refer to some Chinese room or stochastic parrot arguments that I won't go into in detail. But then, surprisingly, over the last 3 years, my view has changed. And it started, and so apologies for this detour into language for a while, if this is a robotics seminar, but you might find it interesting. It started off with a bunch of my students, co-advised by the colleagues you see there, who were interested in multimodality in parsing. And they were all excited by a recent series of award-winning papers in EMNLP, and ACL, and conferences like that, which had shown that when you're trying to solve parsing tasks, it turned out that having pixels as a feature just dramatically improved the performance over all the previous methods, the traditional NLP methods. And you can see why. It's cool to think that like perception of the world could help even in a task like parsing. Like, do we know whether the cat is on the table or the cup is on the table or both? It turns out priors about the world are useful, and you could get those through pixels. And so my students knew a good thing when they saw it. All these other award-winning papers, they got on the hunt for another award-winning paper, and they said, what we can do, we can bring more powerful features, we can bring LLM embeddings. Clearly, everything will get better. It did. They were very happy until they actually looked closely at the results, and they actually saw that once you added semantic features, like these features that were coming out of BERT, and then eventually more powerful models, actually just the semantic features alone, the text features alone, blew away the vision features. Or in fact, adding the vision feature back didn't even help, hurt. So that was weird. It kind of was a real, like for a person who's interested in multimodal models, kind of hurt. I want my pixels to matter, and here they started not to matter. Oh well, maybe that's just this one little thing. Except it wasn't. As I'll show you in the next few slides, the next project that we went down in this direction was a little bit of accidental result. We were trying to make diffusion models back in the day, this was about 2 or 3 years ago, not be as I should just say suck as much as they did. Right? Back then, diffusion models, state-of-the-art models, often really didn't do attribute binding very well. They would you ask for an orange dog, it would throw some orange object in the scene, but no, not even a dog. They were very poor on spatial relations. They would have a hard time with attribute binding and gender in this example. They would just never dress the woman in blue, always in red, and so on and so forth. And so this was a problem. And one of my students, actually in a class project, very quickly found, he's like, wait a minute, I see that even LLMs can sometimes talk about the world and know what's bound with which. Well, maybe I could just combine those two things. And he turns out actually just conjuring a prompt from an LLM could really help a diffusion model that was generating pixels. Now, the diffusion model had been trained on tons of pixels, but the LLM has never seen a pixel. It's only seen text. And it's outputting some structure, which turns out to be very similar to what I would call a scene graph. And so this is a first in a series of papers from 2023. You can see they're called LLM grounded diffusion, where we basically showed that you could take an LLM and very lightly prompt it to generate structures that were scene graphs, and then you could condition diffusion models on those scene graphs and get much more high fidelity generations. Now, obviously this was 2 years ago, this field's moving fast. By now, these enormous models have been trained on this, and certainly you don't need this hack to make current models succeed. But we were state of the art for a couple weeks or days or months. And now it's still an interesting point to look back and say, wait a minute, that's evidence that the text-only model kind of could generate a scene graph, which again, 3 years ago, if you'd given me a checklist, or if I was defining the word grounding in front of a class, I'd be like, nope, grounding, text-only models aren't grounded, don't know about scene graphs, they don't know that planes are in the sky, they don't know that boats are in the ocean, they don't know what the texture of the ocean looks like, so on and so forth. Of course, I could get into details about how you take a scene graph as conditioning to improve a diffusion model. There are a lot of papers on that out there, including the one that we published. But once you do that, it all gets better. So suddenly we would have attribute binding just by adding this conditioning that came from a text-only model, which now I have to conclude kind of does know about scene graphs. Somehow from all the text it's read, it understands how to reason about the world and generate women dressed in blue. And it also worked for video. Again, this was pre-Neo and pre-all the latest ones. So the state-of-the-art models were incredibly bad, and ours were just way less bad. But the state-of-the-art models couldn't even put one object on top of another, or make the thing fly in the right direction, or this was its Pikachu, and didn't really look like a Pikachu. And so our just a simple combination of a model that had never seen a pixel and models that could generate pixels but didn't understand structure seemed to give a lot of leverage. So now I'm concluding that these text-only LLMs know about scene layouts, and they know about motion graphs. And so it makes me really question what kind of visual perception is already in an LLM. And so what, of course I can't go too far, right? Human pose and pose tracking, that's a computer vision person problem. We're never gonna have that if you talk to Alyosha at Berkeley, he's like, he doesn't know about stepping upstairs, and it doesn't know about one hand touching the other, interacting, or does it? And so the very last paper in this series is something we published, I think at CVPR this past summer, but it's been out on archive for a year, which actually asked that question. Do text-only LLMs know about human pose interactions in a way that can usefully improve perception of human pose over conventional computer vision baselines? And I wouldn't be showing this slide if it weren't the case. And after the fact, it's not surprising to me at all. Like traditional computer vision folks, and probably even traditional roboticists, would be like, how do I estimate human pose? I got to do some sort of structure and multi-view reconstruction. I probably have human shape priors, maybe multi-cameras. I'm going to collect a data set. I'm going to go read Michael Black's papers. I'm going to have people in a dome. Great, so let's start putting pairs of people in a dome. I think there's one of those at CMU and one of those in Michael's lab. And great, let's collect. How many times have I put a bride and groom in those? Probably 0, or a small number. So there aren't even data sets to go learn from traditionally. And so once I say all that, it doesn't surprise me anymore to realize, actually, if you go read a lot of text, you're going to find a lot of descriptions about human pose and how people interact. So maybe these text-only models actually do know a little bit about interaction of body pose in certain actions and multi-person configurations. And that's what we showed in this recent CVPR paper. Here we're using an LLM, but there are ablations with LLMs. To see that just using a VLM alone can get you a significant amount of signal. It can tell you some important constraints or what to pay attention to. And you can then add that to a traditional pose estimator, which will get more accurate multi-party pose and contact and information like that. So if you're interested in that, the paper was called Pose Priors from Language Models. And it's on archive and I believe at CVPR. So that's kind of rounding out the philosophy part of today, which is, first of all, don't worry, vision, language, and robotics, it's all the same. We're all going to be competing with each other, and that's probably a good thing, and it's historically consistent to return to our roots. And actually, you can poo-poo language models, but we don't even, it's very hard to prove what they can't do. And so I'm more convinced by experimental evidence than argument about the power of different kinds of models out there. And there's a lot of signal in some of these text models that common sense knowledge and knowledge about what I would have said is grounding than I previously expected. Maybe I've convinced you as well. So that's cool, that's philosophy. Now I'm going to spend the next maybe 20 minutes telling you about just cool stuff that's hopefully useful to roboticists, definitely useful for our robotics projects. And it's going to kind of be on this continuum of trying to make VLMs and VLAs either more robust, able to work at higher resolution, and then pushing towards some of the major paradigms of learning and control, either world modeling in the first instance and data-driven imagination, or behavior cloning with explicit reconstruction of 3D structure and human motion. And that'll be video mimic before I close with this sort of 4D pre-training and some of our work called Star Trek and Armor. So this will be a little bit of a kind of set of spotlights, and whichever one you're interested in, feel free to ask me a question or read the paper. Once you start using these models, I just said the power of these models is how strong these priors are, because the text-only models seem to already know a lot. As soon as you do that, you start noticing and then worrying about hallucination, because the text priors are so strong, they'll just start to make stuff up. Or it's not even making it up, it's quite reasonable that there's a refrigerator in the kitchen, right? There probably is, it's just not in that image. And when we're talking about an image caption, we usually want stuff that's in the actual, there's some pixels to support that, right? Or at least we could, that's how we define this problem. And so you want to try and find places where the prior is dominating the pixels, the observation. And perhaps you want to undo that. Here, I'm intentionally giving you a very small image, so you're probably suffering just like a VLM with a 225 by 225 encoded feature, and the boy is sharing his umbrella with what? With a dog, right? Isn't that what always happens? Except if you really look closely, it's not a dog, and it's not, yeah. So, and these models you can ask it after the fact. Sorry, I'm missing a slide here. The first pass through the VLM would say, the boy is sharing his umbrella with a dog, but it's actually not a dog, it's a cat. And then if you, after the fact, say, well, kind VLM, are you sure? Even just asking the same VLM, are you sure that that's actually a cat? It'll probably say, oh, wait, sorry, kind sir. No, I was so wrong. I humbly request you. Let me correct myself. That's actually obviously a cat and a frisbee or something like that. So the same model actually can notice that it's wrong even when it generated something that's correct. That motivated us to try and find an inline architecture which could, on the fly, as it's generating tokens, generate confidence tokens that say, wait, am I sure about what I just said? And when I'm not sure, backtrack until I am sure and regenerate. So we'd like to do that. And it's inspired by some of the ideas that were called retrospective thinking. Oh, here's the slide that I was thinking about. No, so never mind. So we build this architecture called reverse, where we generate tokens. In this case, perhaps we generate an incorrect token. The boy is sharing his umbrella with a girl. And we would like the model to then immediately say, wait a minute, I have low confidence about that, and I should backtrack and keep backtracking until I generate a token which appears confident. And I know it's confident because it generates a token that says it's confident. So this is kind of magical. I've defined the goal. How do we actually build that? Well, it turns out once you describe this idea, you can actually build it in a straightforward way just by constructing a training set that has that property and training a model to do it. That was sort of surprising to me. So the key idea is to go out and have data, tag the noun phrases in the data. And of course, in the ground truth data, we tag the noun phrases with something that says this is confident, because it is confident. And we go out and construct negative data where we change the noun phrase to be something that's not in the image, and we label that as an unconfident or incorrect object. And we can do this for a variety of different things. You can change the number of baseball players in a baseball image. You can change the style of an object, for example, in this airplane image. You can change a fact like the author of the book. And so now I have a data set where when things are wrong, the model says it's wrong. And when things are right, the model says it's right. And I can then fine-tune a model with this structure. And lo and behold, the model will generalize. And now, when it's not quite sure, it'll actually tell us it's unconfident about this. And then we can then, at inference time, as something is generated, we can monitor the likelihood that the next token that's going to be produced is that unconfident token. And whenever it suddenly pops up to be high, we can say, let's skip that and try again and generate a different token. And suddenly it generates a token that then the next token is not going to be the unconfident token. It's going to be the confident token and keep going. And you can either use rejection sampling or query writing, and it works in a lot of good, useful cases where otherwise models would have hallucinated, and you can trade off the expressivity versus groundedness. And we also have some extensions of this to robotics. And when you ask for something that's not there, the model should be aware that the object's not there and backtrack to something else. I'm going to skip over that in the interest of time. So if you're interested in that in more detail, check out this paper. The algorithm's called Reverse, and the title is Generate but Verify, Reducing Visual Hallucination in Vision and Language Models with Retrospective Resampling. And I think the robotics extension is going to be on arXiv soon if it's not already. So that's one cool thing. Like, I think reducing hallucinations gets us a significant way towards acceptance of these classes of VLMs in real hard problems, like in real robotics problems. Another thing we probably need to do is not be limited to relatively narrow views of the world. I think like my earliest work in robotics was building depth cameras for robotic sensors, robotic systems. And we knew you need to have lots of pixels to get accurate information. And if you're looking out at the world, we'd like to not just be limited to 224 by 224. We should probably be able to take 4K by 4K or 8K by 8K. This is work led by my student Baifeng Shi as part of a collaboration with NVIDIA. And I don't probably have to convince you that it's going to be hard to brute force scale your way to this. Like, okay, even if you believe in data space scale, eventually these exponential things catch up with you. If I'm trying to scale to 4K by 4K, and I want to ask questions about little details in the scene, like what's the name of that sailboat, first of all, you're not going to be able to answer the question at low res. And if you try and just brute force run it at high res, or you've got some robotic scene and you want to, count how many protrusions there are from an object that you need to manipulate, well, clearly we're not going to do this with brute force. And clearly anyone who's been around vision for more than a few decades knows, well, come on, think about how every other biological vision system solves this problem, or how we've been thinking about it for decades in computer vision. We should be attending to the things that matter, looking at them at higher resolution, and processing them. Except that's hard to integrate with it just sounds like I bought a whole bag of inductive bias that nobody wanted to have. And so that hasn't been fashionable lately. And we already know what attention means. Attention is the cross-attention of a transformer that's fully connected to everything, right? But here I want to have a different kind of attention. I want to attend to attention. So I want to actually have computer vision or human psychophysics style perception and say, let's figure out where I should look so that I can actually have higher resolution. And yet do this all in a data-driven end-to-end way based on transformers. So there's a lot of data. I won't go into this in the interest of time in this talk, but it's not hard to go out and construct very overly annotated images at high resolution with detailed descriptions all over the place. And once you have that, to train a model that basically can have multi-resolution tokens. So I can have low-resolution tokens that are essentially at 224 by 224, but I can also chip up my image and send the 4K by 4K image into almost the same encoder and get high-resolution tokens corresponding to subregions. And now the game is, which of those should I decode? I can't put them all into, I can't train with all of them. That gets that explosion of complexity. I want to discover which are the ones that are salient, either for this image or for the task, the prompt, and selectively decode those and put them into an inference path. And so this is the figure that I like the most that summarizes this VILA HD model with the sort of PS3 architecture, which takes an image at low resolution. Those are the tokens on the left, the kind of cyan green tokens, and some text question or query. And then it decides, based on all of that, where to look. And it generates a token that then goes out and causes other tokens to be put into the decoding stream, these high-resolution orange tokens, right? So we now have an integrated architecture that's end-to-end trainable that generates a token. It's actually similar to the previous idea. We have a retrospect token or a confident, unconfident token that decides whether or not to backtrack. Here I'm generating a token that decides what other tokens to insert into this stream. It's kind of like a RAG architecture, but it's in coarse-defined, multi-resolution perception architecture. And this scales elegantly and has the desired properties that you would like. I'll refer you to the paper to look in detail at these results. And I'll just show you this video, which I think is one of the, NVIDIA was interested in autonomous driving. And you might want to ask questions about the driving environment. So you're racing down the road. You want to ask a question about the exit upcoming. You need to read what's on the sign. And if you use a baseline system, the baseline system either is operating at too low resolution and can't see, can't figure out the answer to the question until it's too late, or it's running too slow and it can figure it out, but also too late. Only with this kind of architecture can you operate at a super high resolution and do so efficiently. So that's cool. I think we have two ideas now that really push forward VLMs for real-world tasks, like robotics tasks, reducing hallucinations, running at high resolution. Now let's move on to sort of what are the dominant paradigms of vision for robotics. And I'll show you actually three different ideas. The first being world models, the second being kind of explicit like behavior cloning in detail, and then this 4D pre-training future. So this is a CVPR paper, I think won a best runner-up for best student paper or something, I can't remember. I was just a spotlight. I apologize if I overclaimed there. Navigation world models, led by Amir Bar, and collaboration with Meta, Jan LeCun, and others. And I think this is like, this world model story is somewhat controversial, but I also think it's interesting, and it scales. It's a real scaling hypothesis. It's saying we're building these models, diffusion models, that can predict images, and they can predict images conditioned on previous images in time. And now that I can do that, how far can I push this? If I train it on just images of this, a video of this room, can I then predict what an arbitrary viewpoint of this room looks like without doing SLAM, without doing any explicit 3D reconstruction, no nerfs, but just like train a model to predict the next view conditioned on an action. And increasingly, we're seeing that we can do that. And further, if I can condition on an action, I can now do MPC or the equivalent, roll out multiple futures, decide which future looks like the one that I want, and take that action, and then keep going. Don't worry, I'm not going to say this is solved or the only way to do robotics, but I do think it's exciting to see the progress that's being made. And I think eventually these models will converge with some of the other ideas. But here's where the state of the art is. Obviously, this conditioned video model as world model idea has been out there for quite a while. The sort of Dreamer architecture popularized it recently. And we train a model to predict the next frame of a video conditioned on an action, navigation action and a time point. And train that just from data of either closed worlds or open worlds. So we then give it a start image and a goal image, and we see, can the model hallucinate into the world and decide what actions to take to get to a goal image. And if it's a relatively simple environment, like a fixed room, it works pretty well. And it's probably you could solve this with SLAM, but it's interesting you can solve this purely with a data-driven architecture as well. And what makes it feasible right now, because otherwise it would have been just like incredibly computationally prohibitive, is to not to train a typical diffusion transformer on video, where we're like sampling a new, denoising a new image sample based on the previous frames, but to do it in an architecture that's only conditioned on the past, only fully conditioned on the current frame, and linearly conditioned on all the previous frames. So that's That's important. There's a lot of data we can train from. Here's the illustration of this diffusion process where each frame is denoised. That would have been the prior baseline method. In our new attentions, in our CDT, the architecture is only quadratic on the current image, and it's linear in the number of frames for the previous image, and that makes it scale much more favorably than the prior diffusion transformer for this kind of thing. So this model can follow trajectories in known environments. That's pretty cool. I mean, some of the visualization, it's not photorealistic perfect, and I don't think we're not reporting evidence yet that you can do very precise manipulation or anything like that, but it's interesting to see how well it works and how that it also works in unknown environments, right? Like you actually can totally hallucinate what it would look like if I moved to the right here, and who knows if that's what it should look like, because this is all imagined, but it gives you something kind of crazy. So this is sort of at the boundary of real robotics and hallucination. You can use it for planning and navigation, as I said, with MPC and rollouts, and those results are in the paper. And I think this is probably obvious. You can use MPC and or architectures like this Nomad architecture from 2024, and just use the hallucinated rollouts. Now this is all in known worlds, and pick the one that looks closest to the goal and get state-of-the-art performance on certain current challenges. Okay, so the takeaway from this are generative world models, conditional diffusion transformers, computationally efficient, so you can train this and scale this, and it's this without having explicit structure, learning to act in the world. So the last of these sort of nuggets is if you don't like world models, you probably like this. So I'm going to give you both bets. Whoever we're doing all the work at Berkeley right now. This is much more a computer vision person's robotics, humanoid robotics talk. This is like I'm going to watch humans move in the world. I'm going to watch and recover the structure of the world. And I'm going to learn how to act in the world just purely through passive observation by constructing that world and a simulated environment with reward and training a robotic humanoid policy from watching how people act, right? Obviously, a vision person argues that it's easier to do data collection by watching the world than explicitly going out and trying to collect data. And also you can collect data naturally through, by just watching. And so here is the kind of result we have by watching Berkeley students wander through the environment. And maybe they're a little bit drunk, I don't know. We get robots that also mimic them and walk through the environment. And we call this particular algorithm, we call the capability that this particular algorithm provides contextual control. Because as you'll see as I go through the following slides, we're training a model conditioned on the specific environment. So it's going to be conditioned on the 3D structure of those stairs. It's going to have observed human beings walking around. And so it's kind of the opposite of what many people in humanoid robotics are doing right now, which is to try and construct a single policy that can work anywhere. Actually, in the results in this paper that's just been released, I think it'll be presented at Coral next month, we're training a policy just for this specific environment, conditioned on observations to that environment. As the robot walks around, it's going to do whatever people did in that spot. So I think in a moment, this robot's going to go back and sit on that bench, because that's what, if a person was at the bench, it would sit down. And this was all learned just by watching people moving in this environment. There's no control. Right now, the person's just saying, joystick controlling what direction to go. And whatever direction it goes, it does the action that's natural for that location in the environment. And so how do we do this? We do this by tracking all the things that we can track. We can watch people move in the environment, multiple people as well, watch how they interact with each other. We can reconstruct the environment, And then we, in the environment, train a simulated robot to act in the appropriate way at that spot, being as consistent with the observed human behavior as possible. We call this video mimic. This is sort of a high-level snapshot of the whole thing. It's driven purely by monocular video input. We have, from Anju Kanazawa's lab, 3D reconstructions of human bodies over time. This is a collaboration with Anju's lab, Peter Beal's lab, my lab, and Jitendra's lab. A lot of students getting together to bring this to reality. Very exciting work. And we, of course, track the pose. We recover the 3D reconstruction of the environment. We align those two. We retarget the human motion onto a robotic form factor, and then can render what the robot looks like if it was mimicking the human behavior. And then we can train a policy to match that model, given the simulated observations that the real robot will see at inference time. So this video kind of gives you the, sort of sums up everything that's happening in one shot, reconstructing the world, reconstructing the motion of a person retargeted to the humanoid robot form, and then simulating what the sensors on the humanoid robot can see. And now we're going to train a policy based on those sensors to cause the robot to behave as close as the person did in the real world. And we have the variety of policy learning strategies here, pre-training with just the mocap, and then doing geometry-aware tracking and distilling with root motion, and finally fine-tuning with RL on all of those observations. And so here's again some results of walking around indoors in the Bear Lab building, up and down the stairs, and up and down the stairs of the Bancroft Library at Berkeley. I think you look at results like this, and it looks amazing and cool how much we have, also still how much there is left to be done. And also, as I said, these results are for a specific environment. And obviously, we're going to have to figure out how to train a policy that automatically generalizes to any environment as either a mixture of these policies or by distilling them into a super policy. And for that, I would say just stay tuned for the future. Arthur, Hongsak, David, and Junyi were the lead students on this project. Amazing work. Okay, so in the last 10 or so minutes, let me push a little bit farther. I think the two things that the two kind of paradigms I just showed you our latest results on, the kind of model-based, world model-based approach, and the sort of full 3D reconstruction, behavior cloning approach, they're like extremes. It's cool that we have state-of-the-art results in both, but they also kind of feel a little bit limiting to me. They're either too general in one sense or too constrained in another. And so I'd like to propose something that's a little bit in the middle, and I'm going to call it the 4D pre-training hypothesis or conjecture or bet. And first I'm going to do a little bit of history, again, back into the past, and we see the progression of training of robotic visual learning models, actually this early work that Peter and I, with Chelsea and Sergey, pioneered back in 2015, one of the first deep networks that was end-to-end trainable. And actually one of the small facts that I think led to this model's success that might be overlooked by some is it actually wasn't, the reason this model I think worked was it was actually estimating trajectories in a sense. I'll get back, we didn't call them trajectories back then, but there was an argmax function in that model that made it trainable with small amounts of data. Otherwise, if you look back, you're like, how could you have trained a model there with the paucity of data that you had? It turns out that the architecture there found the peaks of distributions and really returned them over time. And that'll turn out to be relevant, I think, as I look to the future. Then people removed that from the architecture and tried to train more general approaches for pre-training with some success, including mass autoencoder style models, which echo also our previous work that Deepak Pathak led on context encoders. And these started to be used for general pre-training representations, and of course now using transformer representations both for encoders and for LLMs. And we kind of arrive at the state of the art. And in terms of pixel processing, the brute force approaches on pixels still seem to have a tough time scaling as efficiently as text scales. I haven't seen that emergent video model. I mean, maybe the latest kind of Neo and Genie and Veo and all those models, I guess the jury's still out on some of those. But for most of the models out there, and certainly all the open models, we haven't seen pre-training just on pixel features be easy, except maybe at the most biggest corporate scales. We'll see, and the jury's still out on that. And that's because I think all of the work we've been doing has been just too focused on texture in vision. And I'll harken back to the past, the tradition of computer vision, say these pixel features, either 2D or 3D, ignore the most important problem in computer vision. Actually, they ignore the three most important problems in computer vision, which again, I wonder if any of the old timers in the room know what I'm referring to. Actually, it was a CMU phrase from our friend Takeo Kanade, who would say, what's the most important problem in computer vision? Well, the most important problem is correspondence. Does anybody know what the second most important problem is? That's right. And the third is also like real estate. So again, this was a phrase I heard when I was a grad student, and I'm going to say they're, I think, arguably also the three most important ones in robotics. And we sort of have been missing that, except to the extent that we're pre-training on trajectories, or building models that pre-train trajectories. And so that's what I'm sort of excited about right now, is to find ways to use this data-driven pre-training model, because I like models that don't have too much inductive bias, that are task independent, and don't have too many quirky parts and interfaces, and can be somewhat end-to-end trained. But I don't want to be beholden just to a pixel. I want to try and have trajectories. Obviously, if we can go all the way to objects, I'd be happy too. Maybe eventually we get there. We've sort of tried that. And so right now I like this idea of a particle-based trajectory. So we want to find models that can pay attention to how things are moving over time and learn from that. Because if you have these particle-based representations, if you can somehow get them from the video, you're very, very close to state in many robotic tasks. Like if I need to figure out how to move this AV clicker and put it over here into this holder, I mean, that's a pretty hard task if I'm just doing from pixels and texture. But if I tell you the front and end key point of this, and I tell you the two key points here, kind of almost any learning algorithm can get me from here to there by servoing or search or something. And it does seem we're getting very close in computer vision to having a kind of bottom-up, just getting that from the pixels. These are like results from just monocular video, which can do 3D optic flow or 3D optic flow plus correspondence, or long-range correspondence that we call 4D vision. This is one paper that Shenchen Wang and Anju's group pioneered. There are a bunch of other similar techniques at the bottom. And I'll briefly mention one of the latest versions that some of my students also helped Anju's group with, called Star Track. I think that is just, the code has just been released quite recently. Lots of great collaborators on this paper. And basically we're solving the full monocular 3D reconstruction, correspondence, track everything over time, largely in a feed-forward process with suitable training data. And okay, cool. Sometimes PowerPoint blows up here because these videos are so large, but it seemed to blow up and then catch its breath and come back to life, so that was nice. So you can see the scenes being aligned and reconstructed, and we both get reconstruction over time, but also an implicit representation. So every point is aligned back to the 3D coordinate system implied by the first frame, and every point it then has correspondence throughout the whole video. So you know where every point is in 3D and its identity, and that's cool. So was cool until PowerPoint died. So let's try if I can get it back. Good, got through it there. So this Star Trek algorithm is sort of in a series that originates from Duster and Monster. Many of you will be familiar with those terms, but basically it's this new class of methods that's doing feed-forward reconstruction from multiple views, and kind of working very well. And so I think this class of architecture can drive particle-based representations that I'm going to argue are the cool way to do pre-training. Maybe I'll mostly talk about the second paper here called Armor. And so we want to basically take these representations that I call 4D representations, which are 3D plus time, and just pre-train on those. The same way we were pre-training on pixels, we're going to essentially do MAE-style reconstructions and predict the future. And that's this paper we presented at ICML this year called Armor, Pre-training Autoregressive Robotic Models with 4D Representations. And the basic punchline here, I think we've solved a few things. We've certainly not solved most of the problems in the space. I think this is just the first kind of assault on the beachhead, if you will, of this in this direction, and more will be coming soon. But the basic idea of this result is you've all probably seen people pre-train on Ego 4D and use those representations to drive large robotic models or VLAs. We've done that in the past too. Here we basically did the same thing, but instead of doing it on the pixels from Ego 4D, we trained it on the 4D representations from Ego 4D. And so naturally now, not only do I see the texture of the hand, but I actually have the 3D and 4D structure of the hand as it moves through the world. And predicting those trajectories, I argue, is really close to the task, for example, if you're trying to have an end effector mimic the human action in a kitchen. And those are the early results that we have, that just training on Ego 4D alone without substantial in-domain robotic data, if you use these 4D representations, you get a pretty nice result, as you can see in our paper. If you look at the results in detail there, I only have 1 or 2 minutes left, so I'm not going to go through all of this. I'll just spotlight the overall architecture, which is a transformer-based autoregressive decoder that's trying to predict the next trajectory element in this 4D sequence, given the image input and other things like text prompts and whatnot. And this is a LLM language-based model. I think you could, sorry, this is not an LLM language-based model. I think you could extend this also to such models, and that's one of the things that we're working on in the future. And the results comparing to baseline methods, including MVP and Octo and OpenVLA, are in our ICML paper. With that, I'm going to wind down with like 90 seconds left and just say, I hope I've given you this argument about the 4D future and a sort of a middle ground between extreme reconstruction and behavior cloning that I showed you in Video Mimic or pure data-driven world models. These VLAs really are useful. You can make them run at high resolution and de-hallucinate them if you're worried about those two things. And as we come to this unified perspective that we're all doing the same thing in AI, whether it's vision or language or robotics, and haptics should definitely play a role. I didn't get a chance to mention any of that, but it's a lot of Ted's pioneering work I think is going to be very relevant there. And that's another modality that is in the mix. We need to always remember that the knowledge and the data can come from anywhere. And right now, since there's so much text, even these blind models know a lot. I wonder how much in the text already knows what a gel site will sense. And I'll ask that over coffee with Ted later on and see if he has an opinion. With that, I think I will close and thank you for your time.
Thank you, Trevor. Do we have any questions from the audience?
Yeah, thank you so much for the talk. I just had a question about the de-hallucination thing. So you mentioned that there would be confidence tokens that are generated. So is it more likely for them to generate the more confident tokens, or is it like it's very equally likely that it generates like a low confidence token versus a high confidence token? So is there anything on that front? Because if if it just generates unconfident tokens, then that's kind of
Well, it generates a token based on the model, the
yeah.
prior implicit in the model, and then it generates a token that essentially is the check pass. It's like
Right.
it's another token that gets to, it's like in that example where you generate the whole string and you say, wait a minute, was there actually a dog? And the model can somehow figure out on a second pass that there wasn't a dog. The generation of this extra token allows the model to have a second look at what it just did. And apparently that gives it more signal. And the confidence of that token, or the likelihood of that token being generated as CN versus UN, is powerful enough to let you decide to backtrack and try again until you get something that the model both generates and confirms as in a token sequence.
Could I ask a follow-up? Okay. So I meant, so there's no current, at least in that implementation, where the confident tokens, like let's say there's a token which is actually it should be very confident in, or it's actually more accurate. So there's no way that it would actually generate that as opposed to something which it is actually low confidence.
Well, I mean, it will eventually get there because it'll reject until it gets there. Yeah, I think the whole point of this is we haven't figured that out yet.
Okay.
I mean, of course, I think future work could be, well, why don't I take all this data to retrain the model? Maybe it'll get better.
Yeah, sure.
It's probably the next paper in the series.
Okay. Hopefully I'll see it. Thank you so much.
Or you can do it.
Okay, thank you so much. Maybe I'll take one more question.
Hey, thanks for the great talk. My question was from the very last slide. I was hoping that the middle ground between the completely data-driven world models versus database world models would be something like where we use SLAM plus diffusion models in conjunction together. Because, for example, in Star Trek, the example that you showed where the train moves away, there is a hole in the map there, which could be filled with diffusion model, which you have already proven at the beginning of the slides that if you provide structure to any generative model, it produces very good results. So what are your thoughts on that?
Yeah, I think that's, if I'm mapping your question correctly onto the following question of, I mean, diffusion models at scale, especially the very powerful ones that are coming out, may be implicitly reconstructing 4D representations internally. There might be an alternate pathway to this pre-trained future. And so I think we have a few projects on trying to introspect or distill internal structures out of diffusion models. And that might also be a way to get to this kind of representation of the story. But we don't have any results on that yet. So I think it's still TBD, and we'll be interested to hear of other people who are trying similar things.
Great. Thank you.
Okay, that's all the time we have for questions. So let's thank the speaker again.